Two variables can move together without either one causing the other. Correlation is a property of a joint distribution. It measures how much two variables co-vary. Causation is a property of a mechanism. It measures what happens to one variable when you change the other. These are different questions about different objects. A correlation can be high even when there is no causal connection, and a causal connection can produce low correlation under some distributions. The direction of causation cannot be read from a correlation coefficient. Conditioning on an event means restricting attention to outcomes where that event holds. The conditional probability is a ratio of the joint frequency to the marginal frequency. This is a mathematical operation on the observed distribution. No assumption about mechanism or structure is required. Conditional probability answers. Among cases where X took this value, what distribution did Y have? It describes a pattern. It does not describe what would happen if you forced X to take that value. An intervention means externally setting a variable to a specific value. This is different from observing that the variable happened to take that value. When you intervene, you sever the variable from its natural causes. The distribution of outcomes after an intervention is not the same as the conditional distribution of outcomes given the observation. Conditioning observes. Intervention changes the system. This distinction is not philosophical. It produces different numbers. A confounder is a variable that affects both the input and the output. When a confounder exists, the input and output move together even without any direct causal link between them. The observed association reflects the confounder's influence on both variables. Conditioning on the input does not remove the confounder's effect on the output. This is because the confounder acts through a separate pathway that conditioning on the input does not block. The result is that the conditional distribution misleads about what intervention would produce. Conditioning on the input creates a subpopulation, those for whom the input took a specific value. That subpopulation was not selected randomly. It was selected by the same process that produced the data, including the confounder. The distribution of outcomes within that subpopulation reflects both the input and the confounder. An intervention would assign the input value to everyone, regardless of the confounder. These two operations produce different distributions. One is selection, the other is assignment. When a confounder determines both group membership and outcome, aggregating over groups can reverse conclusions. A treatment can appear beneficial within every subgroup but harmful in the aggregate. The reversal occurs because the confounder causes sicker patients to receive more treatment. Conditioning on treatment does not condition on severity. The aggregate comparison mixes two different causal structures. This is not a statistical anomaly. It is the mathematical consequence of aggregating over an uncontrolled confounder. Conditioning is a descriptive operation. It restricts the sample to cases where a particular value was observed. It describes what co-occurs in the data. It does not describe what would happen if you acted on the system. Conditioning cannot identify causal effects when confounders are present. It cannot predict the outcome of intervention. Every control decision implicitly assumes a causal model. Conditioning alone does not provide one.